Hello viewers, I Neelofer welcome you to the chapter of correlation analysis. In this unit we'll study the meaning of correlation and the types of correlation. Before proceeding to study the various kinds of correlation such as scattered diagram, graphic method, Karl-Pearson coefficient, we'll first acquaint ourselves with the terms which are going to be used in this discussion, what we shall discuss about these topics. But we must first understand the following concepts before proceeding further. So far we have studied problems relating to one variable only. In practice, we come across a large number of problems involving the use of two or more than two variables. If two variables, two quantities vary in such a way that movements in one are accompanied by the movements in the other, these quantities are correlated. For example, there exists some relationship between age of husband and age of wife, or price of a commodity and the amount demanded, increase in rainfall up to a point and the production of rice, an increase in the number of television licenses and the number of cinema admissions, etc. The statistical tool with the help of which these relationships between two or more than two variables are studied is called as correlation. The measure of correlation, called the correlation coefficient, summarizes in one figure the direction and the degree of correlation. This correlation analysis refers to the techniques used in the measuring of closeness of the relationship between the variables. A very simple definition of correlation is given by A.M. Tuttle. He defines as correlation as an analysis of the covariation of two or more variables is usually called correlation. Correlation analysis helps in determining the degree of relationship between the two or more variables. It does not tell anything about the cause and effect relationship. Even a high degree of correlation does not necessarily mean that a relationship of cause and effect exists between the variables, or simply stated, correlation does not necessarily imply causation of functional relationship, though the existence of causation always implies correlation. By itself, it establishes only covariation. The explanation of a significant degree of correlation may be due to any one or a combination of the following reasons. First one, the correlation may be due to pure chance, especially in case of small sample. Second point, both the correlated variables may be influenced by one or more other variables. Third point, both the variables may be mutually influenced by each other so that neither can be designated as cause and the other the effect. Types of correlation can be studied under the following heads. First one, positive correlation. The correlation is said to be positive when the values of two variables move in the same direction, so that an increase in the value of one variable is accompanied by an increase in the value of the other variable, or a decrease in the value of one variable is accompanied by a decrease in the value of the other variable. Second one, negative correlation. Correlation is said to be negative if an increase or decrease in the values of one variable is followed by a decrease or increase in the value of the other. Note that the changes in the values move in opposite direction. Third one, simple, multiple and partial correlation. Correlation is said to be simple when only two variables are studied. For example, when we study the height and weight of persons, the resultant correlation will be simple. If more than two variables are studied simultaneously, the correlation is said to be multiple. For example, when we study the price, demand and supply of an article, the resultant correlation is multiple. The correlation is partial when we study the correlation between two variables, neglecting the influence of some other variables on both the variables. Example, the price of a commodity is determined by a large variety of factors like supply, demand, consumers, etc. Now let's come to the fourth one, linear and non-linear. Correlation, that is curvilinear. Correlation is said to be linear if the amount of change in one variable tends to bear a constant ratio to the amount of change in the other variable. Consider the figures related to the following two variables, variable x and variable y. So we have these data with us. The ratio of change between the variables in the above example is the same. This is a linear correlation. The correlation is non-linear or curvilinear if the amount of change in one variable does not bear a constant ratio to the amount of change in the other related variable. The various methods of ascertaining whether two variables are correlated or not are given as the first one, scattered diagram method. It's a chart prepared to represent graphically the relation between two variables. The variables x and y are taken upon the x and y axis of the graph paper. For each pair x and y values, we mark a dot, and dot we get as many points on the graph as a number of observations. By examining the shape of the plotted dots, the degree of correlation between the two variables can be estimated. Following are some scatter diagrams representing varied degrees of correlation, where x and y axes are representing the two sets of variables and r is the coefficient of correlation. Now let's come to the second method, graphic method. When this method is used, the individual values of the two variables are plotted on the graph paper. We thus obtain two curves, one for x variable and the other for y variable. By examining the direction and closeness of the two curves so drawn, we can infer whether or not the variables are related. If both the curves drawn on the graph are moving in the same direction, either the upward or the downward, correlation is said to be positive. On the other hand, if the curves are moving in the opposite direction, correlation is said to be negative. Now that brings us to the third method, which is called as Karl-Pearson's coefficient of correlation. Of the several mathematical methods of measuring correlation, the Karl-Pearson method, popularly known as Pearsonian coefficient of correlation, is most widely used in practice. The Pearsonian coefficient of correlation is denoted by the symbol small r. It is one of the very few symbols that is used universally for describing the degrees of correlation between two series. The formula for computing Pearsonian r is given as r equals to sigma xy divided by n sigma x into sigma y. Let's take it as the first equation. Hence, x is equal to capital X minus x bar and small y is equal to capital Y minus y bar. Now, sigma x is equal to standard deviation of the series x. Sigma y, that is the standard deviation of the series y. Capital N here is the number of paired observations. This method is to be applied only when the deviation of items are taken from actual mean and not from assumed mean. The value of the coefficient of correlation as obtained by the above formula shall always lie between plus minus 1. When r is equal to plus 1, it is perfect positive correlation between the variables. When r is equal to minus 1, it is perfect negative correlation between the variables. And when r is equal to 0, it is no relationship between the two variables. The above formula for computing Pearsonian coefficient of correlation can be transformed in the following form, which is easier to apply. So small r is equal to sigma xy divided by under root sigma x square into sigma y square. So let's make this as equation number 2, where we can see the small x is equal to capital X minus x bar and small y is equal to capital Y minus y bar. Now let's take an example here, example 1. calculate Carl Pearson's coefficient of correlation from the following data. So we have a table of x and y. Now let's see the solution to this. We are doing the calculation of Carl Pearson coefficient of correlation. For that, we are making a table of, with the columns headed x, x minus 18, which is equal to small x, x square, y, y minus 19, which is equal to small y, and y square. Then the last column is xy. So we're using the formula again, r equals to sigma xy divided by under root sigma x square into sigma y square. So where again small x is equal to capital X minus x bar and small y is equal to capital Y minus y bar. So we know that we can calculate from the table that sigma xy is equal to 431, sigma x square is equal to 598, and sigma y square we have calculated as 338. Now apply the formula. So small r is equal to 431 divided by under root of 598 into 338. So that gives us 431 divided by 449.582. So that is giving us a positive value of 0.959. So this was the solution to the example 1. Let's come to the next example 2. Find the coefficient of correlation for the following. We have a table that contains two columns, cost, which is given in rupees, and sales, which is also given in rupees. Now let's see the solution to this. We are doing the calculation of Carl Pearson coefficient of correlation again. So for that, we are making a table with the columns headed as capital X, second column x minus 65, which is equal to small x, third one x square, fourth column y, capital Y minus 66, which is equal to small y. Then we have the y square column, and the last one we have is xy. Again, we are applying the formula r equals to sigma xy divided by under root sigma x square into sigma y square. Now from the table, we can easily calculate sigma xy, which comes out to be equal to 2704, sigma x square, which comes out to be 5398, and sigma y square, which is 2224. So now we are plugging up all these values in the formula, and we get r equals to 2704 divided by under root of 5398 into 2224. So now we are taking the log on both the sides. We have log of r equals to log of 2704 minus 1 by 2. In the bracket we have log of 5398 plus log of 2224. So that gives us log of r equals to 3.4320 minus 1 by 2. In the bracket we have 3.7322 plus 3.3472. That gives us log of r equals to 3.4320 minus 3.5397. So that finally gives us 1 bar 0.8923. So that is giving you 0.78. So this is the answer. Carl Pearson's coefficient of correlation is based on the three following assumptions. First one, in each of the series correlated, a large variety of independent causes are operating so as to produce a normal distribution. Second one, the forces so operating are related in a causal way. Third point, the relationship between the two series is always linear. Let's see the merits first. First one, this coefficient measures both the direction and the degree of the correlation between two variables. Second one, this is amenable to further algebraic treatment. Let's see a few of the demerits here. The first one, it assumes a linear relationship between the given variables which may not be there. Second one, it is liable to be misinterpreted as a high degree of correlation does not necessarily mean very close relationship between the variables. Third one, it is tedious to calculate. Fourth one, it is unduly affected by the values of extreme items. The coefficient of correlation measures the degree of relationship between two sets of figures. As the reliability estimates depends upon the closeness of the relationship, it is imperative that utmost care is taken while interpreting the value of coefficient of correlation. Otherwise, the fallacious conclusions may be drawn. Unfortunately, the interpretation of the coefficient of correlation depends very much on the experience. The full significance of R will only be grasped after working out a number of correlation problems and seeing the kinds of data that gives rise to various values of R. The investigator must know his data thoroughly in order to avoid errors of interpretation and emphasis. He must be familiar or become familiar with all the relationship and theory which bear upon the data and should reach a conclusion based on logical reasoning and intelligent investigation on significantly related matters. However, the following general rules are given which would help in interpreting the value of R. The first one, when R is equal to +1, it means that there is a perfect positive correlation between the variables. Second one, when R is equal to -1, it means that there is a perfect negative correlation between the variables. Third point, when R is equal to 0, it means that there is no relationship between the two variables, that is, the variables are uncorrelated. Fourth point, the closer R is to +1 or to -1, the closer the relationship between the variables, and the closer the R is to 0, the less close the relationship is. Beyond this, it is not safe to go. The full interpretation of R depends upon the circumstances, one of which is the size of the sample. All that can really be said is that when estimating the value of one variable from the value of another, the higher the value of R, the better the estimate. Fifth one, the closeness of the relationship is not proportional to R. If the value of R is 0.8, it does not indicate a relationship twice as close as one of 0.4. It is in fact very much close. The probable error of the coefficient of correlation helps in interpreting its value. With the help of probable error, it is possible to determine the reliability of the value of the coefficient insofar as it depends on the conditions of random sampling. The probable error of the coefficient of correlation is obtained as follows, that is P dot ER is equal to 0.06745 into 1 minus R square divided by under root of n, where R is the coefficient of correlation and capital N is the number of pairs of items. Now the first one, if the value of R is less than the probable error, there is no evidence of correlation, that is, the value of R is not at all significant. Second one, if the value of R is more than 6 times the probable error, the existence of correlation is practically certain, that is, the value of R is significant. Third one, by adding and subtracting the value of probable error from the coefficient of correlation, we get respectively the upper and the lower limits by which coefficient of correlation in the population can be expected to lie. Symbolically, rho is equal to small r plus minus PE, where PE denotes the probable error and rho here, it denotes the correlation in the population. Carrying out the computation of the probable error, assuming a coefficient of correlation of 0.80 computed from a sample of 16 pairs of items, we have probable error of R is equal to 0.06745 into 1 minus 0.8 square divided by under root of 16. So that gives us 0.06. The limits of the correlation in the population would be R plus minus probable error, that is 0.8 plus minus 0.06 or 0.74 to 0.86. The following are the important properties of the correlation coefficient R. The first one, the coefficient of correlation lies between -1 and +1. Symbolically, -1 is lesser than or equal to r, which is lesser than or equal to +1, or we can say the absolute value of r is lesser than or equal to 1. Now the second point. The coefficient of correlation is independent of change of scales and origin of the variables x and y. Third point. The coefficient of correlation is the geometric mean of two regression coefficients. Symbolically, it can be represented as small r is equal to under root of bxy into byx. This method of finding out covariability or the lack of it between two variables was developed by the British psychologist, that is Charles Edwin Spearman, in 1904. This measure is especially useful when quantitative measure for certain factors, such as in the evaluation of leadership ability or the judgment of female beauty, etc., cannot be fixed, but the individuals in the group can be arranged in order, thereby obtaining for each individual a number indicating his or her rank in the group. In any event, the rank correlation coefficient is applied to a set of ordinal rank numbers, with 1 for the individual ranked first in quantity, or so on, to n for the individual ranked last in the group of n individuals or n pairs of individuals. Spearman's rank correlation coefficient is defined as r equals to 1 minus 6 sigma d square divided by n cube minus n, where r denotes a rank coefficient of correlation and d refers to the difference of ranks between paired items in the two series. In rank correlation, we may have two types of problems. First one, where actual ranks are given. Where actual ranks are given to us, the steps required for computing rank correlation are: the first step, take the difference of the two ranks, that is r1 minus r2, and denote these differences by capital D. Second, square these differences and obtain the total sigma d square. Third one, apply the formula r equals to 1 minus 6 sigma d square divided by n cube minus n. Now let's see an example here. Two judges in a beauty competition rank the 12 entries as follows. So we have a table of x and y. Now what degree of agreement is there between the judgments of the two judges? Now let's see the solution. So here we are doing the calculation of rank correlation coefficient. For that, we are making a table of the following columns, that is, the columns are capital X, which is R1, capital Y, which is R2, third one is R1 minus R2, that is equal to capital D. Then the next one is R1 minus R2 square, that is equal to D square. So we are applying the formula as well over here. So capital R is equal to 1 minus 6 sigma D square divided by n cube minus n. So we have from the table sigma d square calculated as 416 and n is equal to 12, we know that. Now plug in these values in the formula and we get r equals to 1 minus 6 into 416 divided by 12 cube minus 12. So that is equal to 1 minus 2496 divided by 1716. So that gives us 1 minus 1.454, which is equal to minus 0.454. Now the second one, where ranks are not given. When we are given that the actual data and not the ranks, it will be necessary to assign the ranks. Ranks can be assigned by taking either the highest value as 1 or the lowest value as 1. But whether we start the lowest value or the highest value, we must follow the same method in case of both the variables. Now let's see an example here. Calculate Spearman coefficient of rank correlation for the following data. So we have a table of capital X and capital Y, the variables X and Y. Now let's see the solution here. Again, we are doing the calculation of rank correlation coefficient. For that, we are making a table of columns X, capital X, which is R1, capital Y, which is R2, then R1 minus R2 square is equal to D square. So we have all these columns with us. Now we are applying the formula R is equal to 1 minus 6 sigma D square divided by n cube minus n. So from the table we have calculated sigma d square is equal to 160, n is equal to 8. Now plugging these values in the formula, we get r equals to 1 minus 6 into 160 divided by 8 cube minus 8, which gives us 1 minus 960 divided by 504. So that is giving you 1 minus 1.905, which is giving us minus 0.905. So that was the solution to this example. Now let's see a few of the merits first. This method is simple to understand and easy to apply compared to the Carl Pearson's method. The answer obtained by this method and the Carl Pearson's method will be the same provided no value is repeated. That is, all the items are different. Second point, where the data is of a qualitative nature like honesty, efficiency, intelligence, etc., this method can be used with a great advantage. Third merit, this is the only method that can be used where we are given the ranks and not the actual data. Fourth one, even where actual data are given, rank method can be applied for finding a rough degree of correlation. Now let's see a few of the demerits. The first one, this method cannot be used for finding out correlation in a grouped frequency distribution. Second one, where the number of items exceeds 30, the calculation becomes quite tedious and require a lot of time. Therefore, this method should not be applied where capital N is exceeding 30 unless we are given the ranks and not actual values of the variables. So finally, we have learnt today the introduction of correlation analysis. In the script, we have learned the types of correlation and methods of correlation, such as scattered, graphic, Carl Pearson's and Spearman's rank correlation. So that brings us to the end of today's episode. We are ending here the chapter of correlation analysis, and we'll see you again discussing about our next topics on more wide variety. Have a nice time. Thank you and bye.